This one started life as a Patreon supporter exclusive on Flight Shops, but it's really cool, nerdy stuff. So I've kind of compiled 2 of the supporter exclusives to make into an episode for you guys here.
Charlie Foxtrot, Charlie Golf Alpha, traffic 2 miles to your west, altitude indicate 4,800 maneuvering.
Yeah, Charlie Golf Alpha looking. I don't see him, but I do have him on the traffic scope.
Roger.
This was the first IFR mission in this airplane, and it was actually on the way to get the prop serviced as well as dynamically and statically balanced at Hartzell. Lots of really amazing stuff that I shared on the Flight Shops channel publicly, but these are a bunch of selects from the stuff that I was collecting while editing. A lot of it did not make it into the public episode, but it's perfect for the pilot nerds here, so enjoy. So I'm good to just fire it up? Yeah, they're coming up. We actually parked the airplane with the flaps down just to remove the temptation of stepping on them when getting in. Anyway, this is actually setting up for the dynamic balance where we'll be running the airplane up to the cruise RPM of 2,400. But before that, I think it's important to see the static balance, so here's that.
The machine is calibrated, and then what we're looking for is a light that signals in the green that the propeller has in fact been statically balanced. We're measuring it at 360 and 180 degrees just to confirm that the balance is good in both planes. If we wanted to check the sensitivity, and we'll watch those numbers here, and I'm actually going to take this dollar bill, we'll see if this works, but we'll take a dollar bill, US dollar bill, and we'll see if this is enough weight to actually change the reading on the machine. So we'll put it was about 196.03, and you can see now that I don't have a green light, but what I actually have is a change on the machine in terms of how much weight that I have to actually add to the other side of this propeller assembly, and that's how sensitive the machine is. Literally a dollar bill is enough to throw the balance out. The benefit of this is when we go to do the dynamic balance, we should be able to bring the rotational group into balance much better than we would if we had a level of static balance, which might not have been as accurate.
That's crazy. Okay, go ahead and take it away, and I'll just let the machine go back to normal.
And you can see it went back to normal, and we have the green light. Literally $1.
Okay, so back to the dynamic balance. The airplane's rigged up with some pretty high-tech equipment. It's wired up so they can plug in the monitor to these cables. And this thing is some sort of a light sensor or gun, I think. I'll get the details when I publish. And there's this reflector on the prop, which is how it senses it. And all the data goes to this monitor computer console thing. We have the tail tied down as well as the airplane chocked. The initial run, I needed to get it up to oil temperature before I could do the run up to the 2,400 RPM. When I gave the thumbs up, they saved the baseline numbers, told me to shut down, and then the process continues with tweaking teeny tiny amounts of weight and then running it up again and seeing what the changes were. Bags off. So the guys instantly knew which screw they needed to remove from the spinner to begin the process of dialing in the dynamic balance.
So right now we zeroed the scale with the spinner screw, and then you measure out your weight. So you got 13.1, it wants 13.17 grams at 340.5 degrees. And here we have a template with where our spinner screws are, which is where we can add weight right now. We can add weight at 340, so that's what we'll do.
So initially they used weighted screws on the outside of the spinner.
And that weight also has the weight of the spinner screw included in it.
Okay.
And then when we're all done, we'll move it inboard on the bulkhead inside the spinner. This machine has a capability of splitting the weight, so we can say, okay, we want to add weight at 190 and 220, and it'll calculate that for us. So it's
cool. All right. So
makes it pretty easy.
So we're gonna fire it up again with that weight added. Okay. Won't be as long waiting on temps this time. So would you consider it a hot start now or not? It's not really super temp yet.
Nah, you're right in between, so your guess is as good as mine. That's why I'm glad you're running it, not me.
Yeah. Yeah. Clear prop. So the key here is to get it to the exact cruise RPM that we desire, which in our case is 2400. Having lever engine controls as opposed to vernier knobs makes it a little bit more difficult to be precise, but I took my time and got it where I needed it. So once I'm confident that it's stable at 2400 exactly, I give them the thumbs up. They save the numbers and tell me to shut down. Eggs off. What do you think?
So we're at 0.3 and we actually added weight and our goal is to get real close to the center. We actually went past a little bit. So we're going to hit our remove previous weight and it'll recalculate and we'll have a lesser weight in that location. So right now we went from 1/4 inch of movement per second to 30 thousandths of an inch of movement per second.
Wow, that's crazy.
And this ought to make it better.
Okay. And then we're going to run it one more time after this adjustment?
Yeah, one more time.
Yeah, okay.
Before it went at 13.2 grams, now it wants 11.5 grams.
So we're taking 2 grams off.
2 grams, wow. How'd they do this in the old days?
This is really kind of the same as when you buy tires for your car and they speed balance it.
Right.
Except you're balancing kind of the engine, prop, and spinner all as one unit.
Yeah, that is what's nice about dynamic balance. I mean, it's statically balanced at the factory, the prop.
Yeah.
It's
You know, but then as a combination, the airframe, engine, prop together is what a lot of times people will say, well, it's been statically balanced, right? And it's like the dynamic balance, you know, kind of puts it all together and makes the whole
in context.
The whole machine smooth, right? Exactly.
Yeah. Ready for me to strap in? Or not strap in, as it were? Clear prop. Mags off, everything shut down. Cool, so that got it?
Yeah.
And these are the final numbers that we landed on. It was 0.021 IPS, which they were very happy with, so I'm impressed with that. It's super smooth now. And that's the weight on the inside of the hub, and you can notice the index mark they made on the bulkhead, which lines up with the spinner, because obviously that's balanced as well. So this stuff came together pretty well for a Flight Shops episode that covered the factory tour as well. But there was a really cool, super technical part that only made it in as a smaller scene into the Flight Shops episode. But this next part from the factory, this is stuff that I just had no idea about. Harmonic vibration testing and stuff. I'm sharing this with you guys raw. A small scene from this made it into the public episode, but obviously this alone is 15 minutes and it's almost non-stop interesting, so please enjoy.
We do a lot of testing of our products. Part of that testing is testing for engine propeller vibrational compatibility. And when we say vibration, we're talking typically about very high frequency vibration that the prop is experiencing, rather than the vibration that you're going to feel in the engine cabin or in the airplane cabin. So it's not your shaking or buzzing that you're going to feel. A prop may feel completely smooth in the airplane and have something very bad happening to the propeller, and vice versa. Your instrument panel can be shaking so much you can't read it, and the prop is fine. It doesn't know what's going on. It's a rotating system on a reciprocating engine with lots of variables that go into how that rotation is happening and what the prop experiences as a result. So each time the piston is going through a cycle, either intake, compression, combustion, or exhaust, that's altering the progression of the crankshaft through its rotation. So even though your tach signal might be nice and steady, so when you're at 2,700 RPM or 2,500 RPM and not varying very much, that crankshaft is speeding up and slowing down and speeding up and slowing down every time that one of your pistons is experiencing those events. And you've got 4 of them in your typical, 4-cylinder Lycoming on your RV. And that feeds itself into the prop. And that creates stress in the prop. And the prop is designed to handle those stresses, and we need to make sure that it does actually handle those stresses. So part of the testing that we do is instrumented testing on the propellers. We have propellers like this. This is the exact same or very close to it model of the propeller you have on your RV14, with all of the different strain gauges that we have put on the critical locations on the blades. So we've got some tip gauges, we've got some mid-blade gauges, we've got some shank gauges, there's a couple gauges in the hub. And all of this gets measured in flight with the engine doing its thing in several different scenarios. Full power static, takeoff. We'll do a prop load, which is basically using the prop to bog down the engine, and also full throttle. Climb, condition that we call gas load, which is the prop driving the engine, which is actually can be one of the higher stress scenarios, especially for the engine. Basically put the system through its paces and make sure that the prop isn't experiencing anything that's harmful. And sometimes what it is, and we'll have installations where we got to fix something, or a lot of times the answer is an operating restriction, because a piece of paper on your instrument panel doesn't really weigh that much and it doesn't really cost that much, but redesigning your prop or your engine does cost a lot. And it can weigh a lot too.
So you're saying you mean like you can't operate this airplane at 2450 RPM, but you're fine at 24 or 25?
Yeah, so there's generally kind of placards that are a result of extra power, or placards that are a result of the gas load testing that I mentioned. So a typical placard can be something like, do not operate between X and Y RPM above Z inches of manifold pressure. Or it may be, do not operate below X manifold pressure with less than Y inches of manifold, X RPM with less than Y inches of manifold pressure. And that's typically a gas load placard. But what that means is we've seen something in the data that shows us there is a range that we need to avoid in order to maintain acceptable stresses on the propeller. And every factor of your engine installation influences what those stresses are. Compression ratio matters. Whether or not the crankshaft has counterweights or dampers, which we'll refer to as undamped or counterweighted or damped. What the ignition system looks like, whether it's an electronic ignition system or standard magnetos. All of that plays into the stresses that the prop experiences during its life.
That's really interesting to me, because I had no idea that ignition could possibly impact a prop. So can you explain to me why or how?
So as I mentioned, every time your piston is moving, it's changing the amount of load that's going into the crankshaft. How stiff the crankshaft is determines how much it flexes as it's being loaded. Everything deforms under load. It's just a matter of how much. So by altering the ignition system, you're changing the characteristics of the combustion that set that piston in motion. So how quickly that combustion occurs over the very short time span that it is occurring, versus a very high energy spark ignites everything at once. You think about the extreme end would be detonation. If you've got too high a compression ratio and the whole mixture goes off all at once, that's a much bigger bang, and it's going to break things in your pistons usually. And that's a bad scenario that no one wants to have in their engine. But that same thing occurs at lower levels of, if you have a really weak spark, your flame front doesn't move very quickly and your combustion is more gradual. It's more of a pacing, more of a measured application of the force from combustion on the piston. Whereas if you have everything spark off all at once, a more complete combustion, then it's going to affect, it's going to happen in a much shorter period of time. It's just going to be a higher impulse, which the prop is going to react to.
Wow, that's cool. That's amazing. So do you actually fly this prop with all that stuff on it?
Yes. So we do two types of testing typically. We have in-flight testing and we have ground testing. The real answer is in-flight testing. So there is we unfortunately don't have a version of it here right now because they're being used elsewhere. But we have a telemetry unit that mounts on the front of the cylinder here using you can see the adapter for it right there on this version. It mounts on those holes up there that these wire harnesses plug into. And it feeds data wirelessly back to a laptop that the test engineer is using to record everything that's happening in flight. So we'll do this in flight, put the airplane through its paces, and then sometimes we do testing on the ground too in order to measure these differences.
And then I guess you have to like balance with all these things on it, and it's...
No, as I mentioned, what we're measuring isn't necessarily cabin vibration balance. You can get into instances where something's very badly out of balance and that'll affect the results, but what we are measuring is not what you would consider a balance vibration. It's inherent to the harmonics of the rotating system.
Wow. Okay, so even if these things cause the 3 blades not to be perfectly the same weight or something, that's not an issue for the type of testing you're doing?
No.
Wow, okay. This is totally educational to me because I assumed it entirely was about that mass balance.
No, the mass will affect some of the dynamics of the system, which is part of why you see the difference between composite props and metal props. You've got a much higher polar moment with a metal propeller than you do with the composite propellers. Polar moment being your flywheel effect, how much inertia the system has in its resistance to changes in rotational speed, trying to speed up and slow down. That'll affect the dynamics of the system. What we're trying to talk about is get people on board with the idea that all of these choices you make when you're picking out the details of your installation will affect the propeller. We're in the position where we can't test everything the experimental market comes up with, because the experimental market's able to innovate things way faster than we can, So we're in the process of trying to characterize the things that we can. We know things that are detrimental to systems, like increased compression ratio increases the stresses. Like there's very few instances where an increased compression ratio doesn't increase the stresses on the system. We may have tested a stock engine, at 8.5 or 8.9 to 1, depending on the engine system. Putting in higher compression pistons, 10 to 1s, for example, is going to increase the stress on the prop. Those stresses may be acceptable, they may not be acceptable. We won't know until we test it. Part of the freedom of experimental aircraft is the freedom to experiment, but there are risks associated with that experimentation.
Cool. Wow, this is like way more than I thought I'd learn about this stuff. That's very cool. Okay, let's get some close-ups to this. Or did we miss anything else that you want to say about that stuff? I think that was...
I don't know, it's a pretty in-depth topic.
That's a lot. These things are... So, are these like accelerometers or what are
They're strain gauges. So it's a small electrical device basically that generates a difference in resistance based on how much it bends.
How much it bends. So what's it measuring bend like?
So it's measuring, a composite prop, it's measuring strain. Basically it's measuring how much the individual fibers underneath here are moving apart from each other or closer together.
Wow, okay. So if you test metal props, it's a different deal.
It's measuring a similar thing, but we're measuring stress in that instance rather than strain.
Stress and strain. Amazing. These words that mean things are different.
Yeah. Well, we're still measuring strain, but it's calibrated in terms of stress.
Okay. Cool. Did we miss anything?
Probably. We have a passion for aviation. We have a passion for experimental aviation. A lot of us are home builders ourselves, but we want people to be safe. So, I mean, we do all this testing not because we're being, super restrictive. Our intent isn't to limit the freedom in experimental aviation. We want people to be safe. We want people to understand the choices that we're going to make, that they're making. We can't police the experimental market. We don't want to police the experimental market. you have the freedom to experiment, but we want to make sure that if you're using our products, you're making that choice informed. You're making an informed decision as to the risks that you're taking. You know, anything in life has risk. Any flying has risk associated with it, but you need to understand what risks you're accepting and what you're going to do or not do to mitigate those risks.
I can tell you right now, I had no idea that my ignition, you know, as the example, impacted the prop. That is news to me, so that's cool to know.
Yeah.
Wow. Okay. So if I wanted, so my configuration, how would I go about even trying to understand how to measure the impacts of my decision with, for instance, my PMAG and my EIS?
Yeah. So that's something that we're working on, because in order for you to make an informed decision, we have to provide information. You think about the system that you configured. You have a split system. You have an EMAG P model and a Lycoming. Okay, well, how do those systems interact with each other? Which one is the dominant system? We're working on characterizing the basic effects of is increased spark energy going to be detrimental to a particular engine propeller combination? Is the variable advanced timing that some of these systems employ, including systems that allow the user to specify whatever timing advanced mapping that they want. Are there limits that we can establish, guidance that we can provide to the market? It's saying this is okay, this isn't okay, this is when you should be worried. Unfortunately we're not there yet. So a lot of times the best answer that we can give is we don't know. It's dishonest to say anything other than that. We can say what we have tested and the information that we have about the system, and it's up to someone else to make the call. Like, if you want to make sure that you're completely within the bounds of what we have determined is acceptable for the propeller, then you have to use a system that we have tested. We're working on expanding that in recognition that the market is desiring things other than, for example, stock magnetos on everything. But until we get the data, we can't give you the true engineering answer of what the impact is, unfortunately.
Yeah, that's fair. Okay. So you want to bolt that thing on my plane and go fly it and see what we got?
So that's part of what we're going to talk about. Yeah. Maybe. There are some challenges associated with doing that. We're certainly interested and open to it. Part of it is the airworthiness side of it. It's probably easier to do that in Canada than it is here, doing work on an experimental Canadian registered airplane in the US.
Yeah. I don't know what that even looks like.
Yeah. So it'd be easier for us to send engineers to you probably than to have you come here, although it's harder for our engineers to do it away from home than it is at home. Yeah. Part of the question is your engine configuration something that we want to test? In that it always turns into an optimization game of there's so many configurations out there. If you order a Thunderbolt 390 through Vans, or you order a 390 through Vans, well, you can get a 390, you can get the 390 EXP 119, you can get the Thunderbolt of either one of those two configurations, and you can pick the ignition compression ratio that you have. I think they have 3 options for that right now. You can pick the ignition system. So just within one propeller and one engine displacement, we've got 3 compression ratios and 5 ignition system combinations that you could have. You could have mags, you could have dual EMAGs, you could have dual Lycomings, you could have a Lycoming and an EMAG. You could have none of that. You could have light speeds on it instead. How many of these things do we want to test? How many can we test?
Because it's exponentially.
Yeah. So we are going to have some discussions internally about what things we want to test, and can we figure out what the worst case is and test that and say, okay, anything below some line here is okay. We don't know yet.
And this shot I used at the end of the first Pilot Nerds episode, but anyways, it's so cool I thought I would use it again. Thanks for watching if you're still here to the end, and please let us know in the comments what you'd like to see. We've got a lot of original content coming from Pilot Nerds, but I do have some things in the can that I'll be sharing as well to keep the content flowing. And until next time, stay nerdy.